Okay, so let's see a little bit more of a practical example here, more of a story, and then I'll do this both the transformation method and the CDF method. Okay, so here let's imagine a situation where you're going to get some product. So this is a waiting time. How long is it going to take? Okay, so the total amount of time that it takes to get this product is being called x, variable x. Okay, so that's going to be an exponential distribution, and you can see that here in the future. We're also going then to define the time it takes to, once you picked your product, to get in the line and to pay for it. We're going to call that y. So here, x is the total amount of time, and y is just the amount of time spent trying to get the product by purchasing and waiting in line. So the joint distribution of x and y is given here. It's just actually really just depends on x mostly here. It's waiting time. However, the support, the minimum it can be is the amount of time it takes to actually purchase, to be in line and to carry through with the transaction. So the minimum amount of time is y, and then it can go off to infinity. So it's similar to exponential, but here you can see there's a little bit of difference here. That's why it's not a perfect exponential. What we're wondering about is how long it actually takes to find the product. Okay, so to actually find the product then is going to be the total amount of time minus the time it took, excuse me, to stand in line and to get the product. So how long did it take us to actually find what we were looking for? Or in other words, z. So z then is the transformation. It's the total amount of time minus the time just spent in logistically owning the item. Okay, so here let's rearrange this in terms of x. Let's get let's isolate for x, which gives us the inverse function of x. Okay, so here's x, and then it equals z plus y. We could also find the inverse function of y if we isolate for y. So maybe either of these two could be useful for us depending on which way you want to do this. Okay, so the other thing that we need to do is, of course, consider the limits. Okay, so we know that y is smaller than x. Here, x, we have actually determined x in terms of y and z. So let's just sub that in there. And then we can just subtract y from all sides. So we've got negative y is less than 0, which is less than z, which is less than infinity. So here what we found is that z, of course, is positive. That actually is not surprising when you understand what z is. I mean, the amount of time it actually takes to find the product, of course, must be positive. What else can we do here? We can sub in what y actually is. Okay, so the inverse function of y is x minus z. So we can sub that in here, and we can play these tricks again. Here I'll add a z to all of these things, and I can find out that z, of course, is less than x. That again isn't surprising either, because x is the total amount of time, so z is less than x. Here, when we are making a graph of this whole thing, then we know which area we're actually looking for here. So here, if z equals x, that means it found, it took you 0 time to find the product, and then everything was just spent, all the time was spent in the lineup. Then here's the minimum time it could have taken, all the way up to infinity. Okay, so that's the bound that we're looking at and that we're interested in. Here, let's find the distribution of just z then. Okay, so here I'm going to find the joint of x and z and then integrate out all of the x just to be left with z. So here then the joint between x and z we can find based off of the joint of x and y, where here anywhere there's an x, that's fine, but anywhere that there's a y, we're going to put the inverse function of y and then multiply the whole thing by the absolute value of the derivative of the inverse function of y with respect to z. Okay, so here's the joint distribution. Actually, there is no y. If there was a y there, anywhere where there's a y, we would sub in this variable, these variables here. Then we're going to multiply by the absolute value of the derivative of this with respect to z, which you can see ends up being -1. So the absolute value of that is going to be +1. So here the joint distribution of xz is actually also just e to the -x. So that's the joint distribution. From this picture, we see what we're really interested in is here integrating from this point here, from z all the way to infinity. So from z to infinity of that joint distribution, we take the integral and we can find that it is actually e to the z. So here the marginal distribution of z ends up being f of z, e to the -z, where z, of course, is anything positive. So that's the transformation method. I'm going to also do the exact same question, but with the CDF method, and we should obviously get the same answer. Okay, so with the CDF method, here's the transformation. Let's make sure that we've got both inverse functions, just because that's going to be quite nice to do. We've got here our graph is in terms of z-axis and x-axis, and that's because we're using here the joint distribution between x and z. That gave us the limits that we were looking for because they depended on z and x. Here, however, notice that when you're using the CDF method, here you're using the joint distribution based on x and y. So instead, let's regraph this, but in terms of the y and the x-axis. Okay, so here x can equal y. So if y, if the minimum amount of wait time in line is 0, then x will equal y. That's the minimum, and it can go all the way up to this point here. Which would be what can y be? It can be the maximum amount of time spent is all in finding the product and none in actually paying for it. I'm not sure if I said that right, but anyways, something about that. Anyways, so here this bound is in between. Here this line x equals y. And then the maximum that y can be, I think I said minimum, the maximum y can be would be here is x minus z. That's the maximum y can be. Here's the minimum y can be. So anyways, y is bounded between these two lines. Okay, where did I get this from? Well, it's this transformation right here. Okay, so there's the minimum and here's the maximum that can be. All right, so messing around with the CDF. Okay, so the CDF of x is, of z is less than or equal to z. Z, another way of saying z is just x minus y. So we'll simply sub that in there. Here I'm going to arrange all of this just for x. You could do it for y if you wanted to as well, but here I'm going to do it with respect to x. And so here you can see that this is, I'm interested in where x is less than or equal to z plus y. So what region are we talking about here? Well, there's the two bounds right here and right here. So where x is less than or equal to z plus y, and where y is less than z. Okay, so I've tried to say that logically, where the minimum amount of purchase time is 0, and the maximum amount of purchase time here is total minus find. But you could also do it just from the strict boundaries that we've been talking about here. Anyways, the CDF then is the double integral of the joint distribution of x and y, which we know about right here. And then here you can choose your order of integration if you like. Here what I've done is on the inside I'm doing x, on the outside I'm doing y. So here y goes from 0 to infinity, so it's from this point to infinity, and then I am going to hit this line, and then I'm going to hit that line. So first I hit x equals y, and then I hit x equals z plus y. You could have also done a different order of integration here. You could have gone vertically if you wanted to. But you could see if you were to do that, there would actually be two separate double integrals here. You would have to split it up into two parts. So I think it's a little bit more efficient to go horizontally rather than vertically. Anyways, here's the order of integration that I chose to give me the CDF of z. And then if I take the derivative of the CDF, I of course find the PDF, which is no coincidence that, of course, it gets you the same answer as the transformation method. Furthermore, if you were interested in the moments of Z, then you could integrate here the PDF and multiply it by the particular moments that you're interested in, and you could find that it might be good practice because, of course, it's you can use the gamma distribution to integrate this. Finally, the last note is that you can't use the MGF method here because the MGF method only works when the variables are actually independent. So here you can see x and y are not independent. Also, when you're using MGF, the whole point is that you want to have a sum of random variables to be your transformation. Here we've got a difference of random variables, so that also is not going to help us.